Today we will be discussing magnetic fields and how they can accelerate a magnet. We will then test it for acceleration and velocity to visualize its effects. Magnetic fields are a vector field. This means they have a direction and force associated in the field. A magnetic field is created through the motion of electric charges. The force of a magnetic field moves charged particles in a circular or helical path. In a permanent magnet or solenoid carrying a constant current in a single direction, the magnetic field is stationary. At any given point within the magnetic field, the magnitude and direction remain the same. The opposite is true for a fluctuating current. Materials required to measure velocity and acceleration through induction are the following: a dipole magnet, retort stand, plastic tube, insulated copper wire, electrical tape, retort clamps, and oscilloscope. Construction of the setup begins with placing the retort stand on a solid foundation. Connect the oscilloscope to a power source. Next, the solenoids are created by wrapping the copper wire around the tube. Wrap such that the copper wires are touching each other, leaving minimal gap without overlap. Start by creating one solenoid. Once the first solenoid is complete, fasten the tube to the retort stand using the retort clamps. When the construction is secured, connect the negative and positive terminals to the oscilloscope to the copper wire at either end of the first solenoid. Drop the dipole magnet through the tube and record data read on the oscilloscope. Repeat this until satisfactory results have been gathered for velocity measurements. To test acceleration of the magnet, another solenoid was created located below the first. Connect the positive and negative terminals as done before and record the length of each solenoid and the time taken for the dipole magnet to pass through the tube. Use this to calculate the acceleration induced by the magnetic field. For the calculations, the formulas for velocity and acceleration were used to find the acceleration of the magnet. The velocity under one solenoid was tested 3 times with very similar results. When calculating acceleration, the velocities of each solenoid was measured, and then by finding the change in velocity, acceleration was found. Uncertainties were calculated as a result of potential error, but ultimately doesn't affect the final result, as we are testing if the acceleration changes under the influence of a magnetic field. Results of the demonstration showed that the acceleration of the magnet within the field was less than that of gravity, which meant the magnet decelerated. This shows the effect of magnetic fields on magnetized objects. Acceleration was 8.6752 meters per second, and the velocity through solenoid A was 1.5385 meters per second, and solenoid B was 2.0833 meters per second. The sensor being used in this demonstration is an oscilloscope. This device measures the voltage over time. The sensor specifically detects changes in voltage and is why the graph responds when a magnet is passed through the solenoid. This sensor works well as it accurately keeps track of the time and quickly detects the change in voltage. It can be set up to pause when a change in voltage is detected. This means that results can be analyzed easily. However, the sensor could be better as it is limited by what it can measure. High amplitudes can peak outside the measurable range of the oscilloscope, giving results that cannot be properly analyzed. Another shortcoming of the oscilloscope is that there is no storage memory available. Because of this, comparisons between data cannot be drawn between tests on this device, leaving potential error when transferring data across to a different medium. When measuring time, it was between the peaks presented on the oscilloscope. At these peaks is when magnetic flux is at its maximum or minimum, depending on the position relative to the origin. Between these peaks gives the time in which the magnet was passing through the solenoid. That is because magnetic flux is at its maximum when the magnet is immediately next to the coil and at its minimum in the opposite circumstance. The results show the effects of magnetic field in the opposite form than originally stated. Between the two solenoids, the dipole magnet was decelerated, falling at a slower speed than gravity. This effect can be contributed to the motion of the electric charge through the solenoid, more specifically the charge output from the oscilloscope and the position of the positive and negative terminals. Because of the direction of the magnetic field repelling the magnet would have opposed this due to the side facing and have been decelerated because of the repulsive force between the solenoid and the magnet. Human error was present in this experiment in terms of measurement and calculation error. This brings a degree of uncertainty that must be incorporated into the results to make sure it is promptly accounted for. Due to these sources of potential error, a margin for distance and time has been accounted for that sufficiently supports the requirements of this demonstration. So, it can be summarized that a solenoid can be used to induce a magnetic force which can be further applied to interact with magnetically oriented objects, as well as the oscilloscope having some shortcomings being its measurable range and the memory of the machine.